Welcome to The Explainer. Today, we're diving into something absolutely mind-bending. We're talking about probability in quantum physics, and we're going to explore exactly why reality itself, well, isn't certain. If you've ever thought the universe runs like this perfectly predictable ticking clock, get ready, because the quantum world is about to completely flip that perspective upside down. So think about this for a second. Is reality governed by certainty, or is it all just chance? In our day-to-day lives, we totally expect certainty, right? We figure if we know the rules of the game, we can predict exactly what's going to happen next. But as we're about to see, the deeper we zoom into the fundamental building blocks of our universe, that comfortable feeling of certainty, it literally just vanishes. Let's set a baseline. Just imagine flipping a standard coin. While that coin is spinning up in the air, you know there's a 50% chance of heads and a 50% chance of tails. But we inherently know that once it smacks the table, it's definitively one or the other. We really only use probability here because, well, we don't know the exact force of your thumb or the wind resistance in the room. It's just a handy stand-in for our own lack of information. But man, the quantum world takes this basic idea and does something unbelievably bizarre with it.
Check out this huge divide in physics. Over in the classical world, if you kick a soccer ball and you know its exact speed and direction, Isaac Newton's laws tell you exactly where it's going to land. It's perfectly deterministic. Everything makes sense. But when scientists started looking at the tiniest pieces of matter, we're talking atoms, electrons, photons, they realized these particles completely refused to act like tiny soccer balls. Instead of following neat, predictable paths, their behavior was entirely statistical. The quantum world operates on pure probability and uncertainty. Crazy, right? And that brings us to, honestly, the single biggest misconception people have when they first learn about this stuff. It's so tempting to just think, oh, well, scientists just don't have good enough microscopes to see where the electron actually is. But no, that is completely wrong. It's not a failure of our tools. The particle isn't hiding from us. The jaw-dropping truth here is that nature itself only allows us to predict the probability of different outcomes. So if you were to ask a quantum physicist, hey, where is this electron right now? They literally cannot give you a single precise location. Instead, quantum mechanics gives you pure statistics. It basically says, okay, there's a 70% chance it's here, a 20% chance it's over there, and a 10% chance it's somewhere else. It's kind of like asking a friend where they want to grab dinner, and instead of naming a restaurant, they hand you a probability chart. Before you actually make a measurement, the universe only gives us chances, not coordinates. Okay, so how do we actually describe this bizarre reality? We'll enter the wave function. Before you take a measurement, the state of our electron is described by this wave function, which physicists write out using the Greek letter psi. Think of it like a giant mathematical catalog. It holds all the information about every possible outcome of a measurement you could possibly make on that particle. It is literally the ultimate expression of the particle's potential. Now, a quick heads up, the wave function itself isn't exactly a probability. To get the actual odds, we have to do a little bit of math. We take the magnitude of the wave function and we square it. That gives us the probability density. So if you're looking at a diagram of an electron cloud, those bright, dense regions, that brightness directly translates to a mathematically higher chance of actually finding the electron in that specific spot. So, who actually figured this out? Back in 1926, a physicist named Max Born made a totally revolutionary pitch. He suggested that the wave function should be interpreted as a probability amplitude. We now call this the Born rule, and it is a massive deal. Why? Because without it, quantum mechanics would just be a bunch of abstract math floating around on chalkboards. The Born rule is the bridge. It connects those crazy equations directly to real physical things we can observe in a lab.
All right, talking about math and chances is one thing, but seeing it happen is a whole different ballgame. And nothing shows off this weird reality better than arguably the most famous experiment in all of physics, the Double-Slit Experiment. This is the absolute ultimate proof of quantum probability, and it perfectly shows us how these particles actually move through space.
Picture this. You're firing electrons, just one at a time, toward a wall with two tiny slits in it. If they were just tiny physical bullets, you'd expect them to go straight through and leave two bright bands on the screen behind them, right? But nope. Instead, each single electron travels through like a wave of possibilities, literally interacting with itself. Then, when it hits the screen, smack, it registers as one single dot. But here is the absolute magic of it. If you fire millions of these individual electrons over time, this beautiful, precise interference pattern slowly builds up on the screen. This perfectly nails the paradox we're talking about here. For individual events, there is no scientist on Earth who can tell you exactly where that next single electron is going to land. Its exact landing spot is fundamentally unknowable. But zoom out to millions of electrons, the overall statistics, that grand interference pattern, becomes flawlessly predictable. The individual is totally wild and unpredictable, but the crowd is a statistical certainty. Naturally, this brings up a massive question. Pretty much everyone asks this when they first wrap their head around it. If it's all just probabilities at the base level, does that mean everything in reality is just completely random? Are we just floating in a universe of pure chaos? Well, actually, no. And there's a really profound nuance here. People love to assume quantum mechanics equals total randomness. But the evolution of the wave function itself is controlled by the Schrödinger equation. And get this, that equation is perfectly deterministic. That means if you know the wave function of a system right now, the math tells you exactly what it will look like 5 minutes from now with total precision. The probabilities evolve smoothly. The uncertainty, that feeling of randomness, only pops up at the exact second you make a measurement. We can predict the odds flawlessly. We just can't predict the outcome of one single roll of the dice. Now, as you might guess, not everyone was thrilled about a universe that refused to give a straight answer until you looked at it. Albert Einstein, obviously one of the greatest minds ever, he respected quantum mechanics, but he absolutely hated this probabilistic stuff. He pushed back hard, famously declaring, "God does not play dice." For Einstein, there just had to be hidden gears turning behind the scenes that we hadn't found yet. He firmly believed reality had to be completely deterministic deep down. But his brilliant contemporary, Niels Bohr, fired right back. Bohr basically said, look, nature doesn't owe it to us to make sense to our human intuition. And honestly, history has sided with Bohr on this one. Over the last few decades, we've run incredibly precise experiments, like the test of Bell's theorem. And we're not taking sides on their historical debate here. We're just looking at the source material, and the results are crystal clear. Decades of rigorous tests have consistently backed up the probabilistic predictions of quantum mechanics. Today, it stands as one of the most thoroughly tested ideas in all of science. And hey, this abstract physics isn't just a bunch of nerds arguing at a chalkboard. It literally builds our modern world. Quantum probability is completely essential. Without it, the atoms in your body wouldn't even be stable. Chemical reactions wouldn't work. We wouldn't have lasers. The semiconductors inside the phone or computer you're using right now, they rely entirely on these exact rules. Life-saving MRI scanners in hospitals, quantum mechanics. And that massive future frontier of quantum computing is built directly on this foundation. Without quantum probability, modern tech just wouldn't exist. So, what's the big takeaway from our explainer today? It's this: that cozy, everyday certainty we feel, it's kind of an illusion of scale. Reality, at its absolute foundation, isn't governed by certainty. It's governed by possibility. Tiny particles don't have these pre-written destinies waiting for us to uncover them. They exist in a massive landscape of maybes. It's only when we step in and actually measure them that we force the universe to pick one of those outcomes. The deeper we dig into reality, the more certainty just fades into probability. Which leaves us with one final, totally mind-blowing thought to chew on. If the universe runs on probability, what do you think is actually going on down there? Is reality truly random at its core? Or do you think Einstein was onto something? Are there deeper, hidden rules of physics that we just haven't figured out yet? It's an incredible mystery, and it's exactly what drives physics forward today. Thanks for hanging out with me for this explainer, and definitely keep questioning the nature of our incredible universe.